Hello everyone. Today we'll discuss a topic on instruction format of 8086. So a machine language instruction format has one or more number of fields associated with it. The first field is called opcode and the second field is operand field. That means the instruction, whatever the processor receive from the user or a programmer will have two fields. One is the opcode and operand. So what type of operation the processor needs to do and what type of data is required to do that particular operation will be specified in both the fields. So opcode will tell us the operation and operand will give us the data or the information required by the processor to execute the instruction. So there are different types of instruction formats used in 8086. It can be a 1 byte, 2 byte, 3 byte, 4 byte, and 5 byte, as well as 6 byte instruction formats. Okay, the length of the instruction vary from 1 byte to 6 bytes. So we'll see each type of bytes of instruction and try to understand how they are having a different format in a given instruction. So if the instruction is 1 byte of instruction, so it will be 1 byte long. So it is having 8 bits in that particular instruction. So it has implied data or register operands in it, or it can have complete 8-bit as an opcode, and it can be having the least significant 3 bits of the opcode used for specifying the register operand, if any. Otherwise, all the 8 bits forms an opcode and operands are implied. See here, a sample 8086 instruction format for a 1 byte instruction is shown here. The complete 8 bit is used as an opcode, or else we have a opcode and the register 3 bits lower order bit will be used here. So 8 bit is opcode only, 7 bit plus 1 bit which is for W or Z bit. We will see what is this W and Z bit later. Okay, W specifies the width and Z used by repeat instruction to control the loop. So you can have an opcode which can be of 5 to 6 bit. If the opcode is 5 bit, then the register bit will be of 3 bits. If opcode is 6, then have 2 bits register field. So likewise, 1 byte instruction can be organized. So to understand in little bit in a better way, see this slide. So we have a 8 bit, okay, 1 byte of instruction. Okay, so in that instruction, I'm using all the 7 bits for opcode, and the 8th bit, that is D naught, is either it can be W or Z. So W defines the width. If W is equal to 1, then the data is 16 bit of data. If W is equal to 0, the data I'm going to deal with is only 8 bit. Okay. Mentioned earlier, Z is going to be used by the repeat instruction whenever I'm executing any kind of loop repeatedly inside the loop of a program. Okay. So the second type of instruction format will be, I'm going to use the entire 8 bit as an opcode. Okay, and the third is like I have 6 bits used as an opcode and the 2 bits are used as a register field. So you need to understand that the segment registers are only 4 in number, hence 2 binary bits will be sufficient to code them. Okay, but there are other register which is of 18 numbers, so at least they need 3 bits for coding them. So 2 power 3 means 8 combinations are possible. 2 power 2 means for 4 segments I can have 4 registers, segment register address. Similarly, if the register field is 2 bits means I'm going to address the segment register. If register field is 3 bits means I'm going to address the other registers like AL, CL, DL, that is AX, BX, CX, and DX registers. Even SP, BP, SI, and DI as well. Okay, so the second type of instruction format we are going to discuss is register to register. It is a 2 byte long instruction. So opcode, as I discussed, 1 byte, how it has been arranged, we have seen it in the 1 byte instruction. The second byte of this instruction will have 3 blocks. One is mod, register, and register bar M bar. Mod is MOD, mode of addressing. So here mode of addressing is D7 and D6 bit. So it is 1 1. So it is indicating that it is going to do a register type of operation. Okay, we'll discuss this in detail. Look at this slide. So what did I say? It is a 2-byte instruction format. So we have first byte, which is an opcode. I have a first D naught with a W bit, and we have a D bit. What is this D bit? D bit is a direction bit. Okay, D is equal to 0 means data is transferred from the register. Okay, if D is equal to 1 means data is transferred to the register. So how the data is moving in and out of the register will be specified by the D bit. Okay, so my opcode is having 6 bit and plus D bit plus W bit. So totally 8 bit. So 1 byte of instruction. Now the second byte will have arrangement like this. The first 2 bits, that is D7 and D6, will have 1 1. 1 1 indicate the mode of operation, that is mode of data addressing or data transfer. For example, specifying the operation related to memory or a register will be done by MOD. If you see the table 1, you can understand that if MOD is 00, memory mode is going to be operated. That is, it is going to specify the operation related to the memory, and there is no displacement as such. If 01 is the value present in D7 and D6, the memory mode, again, because it's a memory mode operation, so 8-bit displacement is happening. If it is 10, again it is memory mode, it is 6-bit displacement happening. Now it is 11 now. It is register mode. The operation is specified which is related to register. So D7, D6 is 11 indicating it is a register mode with no displacement. As I mentioned earlier, REG will have 3 bits, D3, D4, D5 and D0, D1, D2, that is register or memory. So what is this? We will see it in the next slide. So let us understand REG. As I mentioned that we have 8 register, we need 2 power 3, 8 combinations are possible. So W is equal to 0, W is equal to 1. 1 indicating it is having a 16-bit data word. For example, if W is equal to 1, if I'm referring to the register DX here, it is a 16-bit register with 16-bit data operated because W is equal to 1. What is the corresponding REG value? The corresponding REG value will be 0, 1, 0 for dx. If it is bx, it is 0, 1, 1. So based on W is equal to 0, whether I'm dealing with 8-bit of data or a 16-bit of data, the corresponding register value can be understood. Okay. So for example, 100, then W is equal to 0, the register is H. So I'm dealing with 8-bit of data. If it is SP, I'm dealing with 16-bit of data and my REG value is 100. This is how you can identify what is the REG value. Okay. Now, to find out the MOD and R bar M fields of a particular instruction, you should first decide the addressing mode of the instruction. Okay. The addressing mode actually depends upon the operands and suggested how the effective address may be computed. From a location, the operand, we need to locate the operand, right? We need to locate the operand and that operand if it is lying in the memory or not. So it is to understand how exactly I'm going to find out this MOD and RM fields, the different addressing modes of the 8086 is listed in this particular table. You can have a look of it. So see here. So R bar M value is here, MOD is here, MOD 00 indicating there is no displacement, but it is a memory mode. 8-bit, it is 0, 1. There is a displacement of 8-bit. Displacement is 16-bit, that is 1, 0. It is happening. Now register operands are there, 1, 1 with W is equal to 0, W is equal to 1. Corresponding registers are mentioned here. Let's say that I'm operating register operands. That means my MOD is 1, 1. So all this no displacement is not going to be considered. So suppose if W is equal to 1, if I'm referring to BX register, what will be the corresponding R bar M value for me? It is 0, 1, 1. Okay. Similarly, if W is equal to 0, and if I'm referring to BL, the value will be 0, 1, 1. Now let's take an example for MOD with displacement of 8-bit. I have a displacement of 8-bit and my W is equal to 1. So 16-bit of data I'm referring to. Let's take an example of SP here. Okay, I'm talking about stack pointer register where I'm displacing an 8-bit of data. So it is SI plus D8. Okay, source index plus D8. What will be the corresponding address? R bar M, that is 100. Okay, MOD is 01 for 8 bit, R bar M is 100, and what is the displacement address? How am I going to calculate? Source index plus 8 bit, and what is the register I'm dealing with? SP, stack pointer, with W is equal to 1. I have a 16-bit data to deal with. This is how you can actually calculate the opcode of a given instruction. The third type of instruction format, which is also a 2-byte long, register to from memory with no displacement. That means I'm going to have a 2-byte instruction. The first byte will define the opcode, and the second byte will tell me MOD, REG, and register or memory addressing modes present in that particular byte of instruction. Okay, here it is similar to the previous one which we discussed, 2-byte instruction, where the mode was specified as 1 1. Here the mode is specified as just a mode. So what are the different types of MOD can be possible in that? We have discussed here in this particular slide. What will be the MOD, what will be the REG values? It has been specified in this particular example, that is registered to and from memory with no displacement. It has been specified as MOD. So MOD can take 0010 or 01 value there. Okay, based on that, register and RM values will be specified looking at that particular table. Okay, now register to and from memory with a displacement. The displacement can be of 8-bit or 16-bit. If it is a 16-bit displacement, I have 1, 2, 3, 4 byte of instruction. The first 2 bytes will be similar to what we discussed previously, registered to from memory with no displacement. Only the last 2 bytes will specify the lower byte displacement and the higher byte displacement. So this type of instruction format contains 2 additional byte for displacement along with the 2 byte, the format of the register to from the memory with no displacement. Okay. Now, suppose if it is having 8-bit displacement, then what happens? It is a 3-byte instruction. The first is an opcode. This is also similar. The second byte is also similar to what we had discussed, registered to and from memory with no displacement. But the last byte will specify the 8-bit displacement. Okay. Now, to understand it more clearly, this will give you a good idea about how it has been arranged. The first byte, second byte, third byte. Okay, the third byte will specify the 8-bit displacement. The first byte will have an opcode. In that, the 2 bits D0 and D1 can specify W bit or D bit. W will specify the bit, D will specify the direction, whether the data is flowing into the register or from the register. So we can have total 6 bits of opcode plus D bit and W bit in the first byte. Second byte can be having MOD, register, and R bar M, that is register or memory. The last byte will have 8-bit displacement. Similarly, if it is a 16-bit displacement, the last 2 bits will be specifying the 16-bit displacement. And how it is going to be specified? The first one will be lower order displacement. The next 8 bits will be the higher order displacement. So this is about register to and from with displacement having 8-bit as well as 16-bit displacement. Okay. Now, there's other type of instruction format which is called immediate operand to register 8 bits. It's a 3 bytes instruction, 1 byte, 2 byte, 3 byte instruction. The first byte as well as the 3 bits from the second byte are used for REG field in case of register to register formats are used for opcode. Okay. Now, see this example. What we saw there, MOD is 1 1 here. Okay, that means I'm doing register to register operation, and instead of RED I have an opcode here. There's a 3-bit opcode specified here. Okay, and R and M will remain the same. It is of again 3 bits. So 3 plus 3 6 and 2 bits MOD 8 bit. This is the second byte, and the third byte will have an operand. So it is a 8-bit operand will be specified in the third byte. So this is a 3-byte instruction. So in immediate operand to register, we can also have 16 bits operand. In that case, the first 2 bytes will remain same as previous example, previous instruction format, which is instruction immediate operand to register with 8-bit. Only thing that we have one extra byte here, which is the higher byte operand. Okay, first always will be lower byte operand specified, and the next will be higher byte operand. Totally, how many byte instruction it is? 1, 2, 3, 4 byte instruction. So remember that in this immediate operand to register instruction format, instead of REG, we will have an opcode, and the MOD will be 1 1. It is in the register mode. Okay. Now we have a 6 byte instruction here. So it is an immediate operand to memory with 16 bits. Okay. Earlier it is a immediate operand to register. Okay. So MOD was 1 1. Now it is immediate operand to memory with 16 bits. So it is MOD will be 1001 or 00. And in between, instead of REG, we have an opcode here. So that is the only difference in the second byte. First byte will remain the same with an opcode. It can have a D or W as well. Okay, specifying the direction as well as the width of the data. And the third byte, fourth byte, fifth and sixth byte will have a displacement as well as the operand. Okay, the third byte will have a lower byte displacement, the fourth byte will have a higher byte displacement, and fifth will have a lower byte of data, and sixth will have a higher byte of data. Totally it is a 6 byte of instruction. So the type of instruction, it might require as 5 or 6 bytes of coding. Okay, the first 2 bytes contains the information regarding the opcode, MOD and R bar M field, and the remaining 4 bytes, 1, 2, 3, 4 bytes will have 2 bytes of displacement and 2 bytes of data in it. So these are the various types of instruction format we have it in 8086. So this slide will give you a so So this is a general instruction format of 8086 microprocessor. So we have 1 byte, 2 byte, 3 byte, 4 byte, as well as you can have another 2 byte for data. Okay, lower order data, higher order data. Totally, we can have 6 byte of instruction in 8086 processor. We know what is D bit. Quickly, we'll have a recap. D bit will tell the direction of data flow into the register, and from the register, W will indicate we are dealing with 8-bit or a 16-bit data or an operand. S bit is this bit was called a sign extension bit. The S bit is used along with W bit to show the type of operation. For example, if I'm doing 8-bit operation with 8-bit immediate operand, then S is equal to 0, W is equal to 0. If I'm doing 16-bit operation with 16-bit immediate operand, then S is equal to 0 and W is equal to 1, obviously because it is a 16-bit operation. Now if I'm doing 16-bit operation with a sign extended immediate data, remember I'm doing a sign extend immediate data, so S will be 1, W will also be 1 because again that operation is 16-bit. Now V bit, this is used in case of shift and rotate instruction. This bit will be set to 0 if the shift count is 1, and it will be set to 1 if the shift count is put up in the register. That means if the CL contains the shift count, we will be set to 1, otherwise it will be 0 if the shift count is 1. Okay, now Z bit, this is used by repeat instruction to control the loop, and if the Z bit is equal to 1, the instruction with rep prefix is executed until the 0 flag matches the Z bit. Okay, when is the 0 flag is set? When the operation results in 0. Correct, that is when the 0 flag is set. So it is going to match with that 0 flag, and if Z bit is equal to 1, the instruction with repeat prefix is executed. I'm going to execute that loop until my value of Z bit is 1. My value of Z bit in a flag register also matches with that. So this is about Z bit. Let's take an example here. MOV AX comma BX. So I'm going to calculate the opcode for this particular instruction. So MOV has an opcode of 1000 10. Now, how do we know that D is equal to 1 and W is equal to 1? Since AX and BX are 16-bit registered, so we will be dealing with 16-bit of data. So default W should be 1 and D is equal to 1 because the instruction says that I'm going to copy a data from BX to AX. So it is from the register, so D is equal to 1. So the opcode for the first byte is 10001011. Next, the second byte, we need to find out what is MOD, what is register, what is R bar M. MOD is always 2 bits and MOD here it is 11 because data is moving from register. Okay, the mode of addressing is register, so we have MOD is equal to 11. Now REG is 3 bits and R bar M, that is register bar memory, is also 3 bits. Okay, now we have to find out what is the REG value. What is, now I'm dealing with AX register here, so go back to the previous slide table. Yeah, so the register is W is equal to 1, the register is AX. So with respect to REG, the value is 000. Okay, I repeat once again, W is equal to 1 because I'm dealing with 16-bit of data. The register is AX. So what will be the corresponding REG value? It is 000. Okay. So I got 3 bits of REG, which is 000. Similarly, the R bar M is also 3 bits. Okay. Now W is equal to 1. What is the register I'm dealing with? BX. So I have to go back and find out. This time I need to find the addressing mode of that particular instruction. Now see here in this table, the operand is which mode? Register mode. So the operands are here. It is 1 1. W is equal to 1. The register was BX. The fourth row here, AX, BX. Yeah, BX is here. And what is the corresponding value of R bar M? It is 0 1 1. Okay. 0 1 1 is R bar M value and MOD is 1 1. Okay, and W is equal to 1 and the register is BX. So R bar M value is 0 1 1. Okay, now put 0 1 1 here. So the total opcode will be 1000101111000011. So if you convert this into the hexadecimal, you get this. So 100 is 8, this is 11. In hexa it is B, 110 is 12, hexa it is C. So 0011 is 3 for us. So opcode for a given instruction move AX comma BX is 8BC3. Okay, this is how you can calculate an opcode for any given instruction. So this is all about the instruction format of 8086.